Welcome to this lesson on voltage regulators. This lesson develops the series voltage regulator from its basic purpose through feedback control, transistor circuits, current limiting and fallback protection. We will connect the circuit behavior to the equations used for setting output voltage and checking device stress. By the end of the lesson, you should be able to explain the feedback action, calculate the important circuit quantities, and recognize the electrical and thermal limits that decide whether a regulator design is practical. A rectifier and filter produce direct voltage, but not an ideally constant voltage. Line variation, load variation, ripple and temperature can all disturb the output. Regulation is needed to preserve bias conditions, measurement accuracy, logic thresholds, and safe operation. Line regulation measures the response to a change in input voltage. Load regulation measures the output change between specified load conditions. Here, NL means no load and FL means full load. A smaller change indicates better regulation. Series and shunt regulators are linear regulators. A switching regulator uses a different energy transfer mechanism. This lesson concentrates on discrete series linear regulators, where the control element is placed directly in the load current path. The series element behaves like an automatically adjusted voltage drop. The sampling circuit returns information about the output. The comparator forms an error relative to the reference, and the error changes conduction of the series control element. When output voltage rises, the control loop increases the voltage dropped by the series element. When output falls, it reduces that drop. This opposing action is negative feedback and is central to both transistor and op-amp regulator circuits. In the simple circuit, the Zener diode fixes the base voltage approximately. The transistor is an emitter follower, so the regulated output is approximately the Zener voltage minus the base emitter voltage. The transistor provides local corrective action. However, there is no separate high gain error amplifier, so the actual output remains sensitive to device parameters and temperature. This motivates the improved feedback regulator. We now analyze the simple regulator. First, identify the assumed model and given values. The Zener is assumed to be in regulation. The transistor base emitter voltage is taken as 0.7 volts and beta is 50. The output follows directly from the emitter-follower relation. The current through the 220 ohm resistor is 36.4 milliamperes. Load current is 11.3 milliamperes and the estimated base current is 0.226 milliampere. The resistor current divides into base current and Zener current. The resulting Zener dissipation is close to 0.5 watt. This demonstrates why a correct voltage calculation alone is insufficient. Component power and derating must also be checked. The improved circuit separates comparison from the pass transistor. The divider samples the output, Q2 compares it with the reference, and Q2 controls the drive available to Q1. The increased loop gain improves line and load regulation. Follow the cause and effect sequence carefully. A rise in output produces a rise in sampled voltage. Q2 then conducts more, reducing the base drive of the series transistor. Q1 drops more voltage and the output is corrected downward. For a falling output, every step reverses. Q2 conducts less, Q1 receives more drive and the series element drops less voltage. The output therefore rises back towards the set point. At equilibrium, the sampled voltage is approximately the Zener voltage plus the base emitter voltage of Q2. Rearranging the divider equation gives the output setting relation. The result depends on the stated assumptions. Substitute the resistor values and reference voltages. The output is 15 volts. As a consistency check, the divider produces 9 volts at the comparison node, matching the Zener voltage plus the base emitter voltage. The op-amp acts as a high gain error amplifier. It continuously changes the series transistor drive until the feedback voltage nearly equals the Zener reference. This generally improves regulation and makes output adjustment straightforward. For the common non-inverting arrangement, the closed loop gain is 1 plus R1 divided by R2. Multiply that gain by the Zener reference. The formula must not be applied blindly. The divider orientation in the actual circuit controls the gain expression. Here, the feedback gain is 4, so the calculated output is 24.8 volts. The input is 36 volts, leaving voltage across the pass transistor Q1. That voltage and the load current determine the transistor power dissipation. A linear regulator converts excess voltage into heat. Evaluate the pass transistor at the worst combination of input voltage and load current and consult its safe operating area curve. Dropout occurs when the input is too low to maintain the control action. A short circuit is especially dangerous because the output collapses while the pass transistor may carry a large current. Current limiting detects the load current and reduces the series transistor drive before the device exceeds its safe region. Excessive load current can damage the series pass transistor Q1. A current limiting mechanism protects the regulator during overload or short circuit conditions. The current limiting circuit consists of transistor Q2 and resistor R4. Load current through R4 develops the sensing voltage for protection. As load current IL increases, the voltage drop across R4 increases. When the drop across R4 becomes about 0.7 volts, the base emitter junction of Q2 is forward biased. Q2 conducts and diverts op-amp output current. The base current of Q1 is reduced. When the base current of Q1 is reduced, the collector emitter voltage of Q1 VCE increases, thereby reducing the load current. Therefore, IL is prevented from increasing further and is limited to a maximum value. IL maximum is 0.7 volts divided by R4. Since VBE of Q2 cannot exceed approximately 0.7 volts, the voltage across R4 is held near this value. To set a nominal half ampere limit, divide the assumed sensing transistor turn-on voltage by the desired current. The result is 1.3 ohms. Its calculated dissipation is 0.325 watt. So a higher rated and suitably derated resistor is appropriate. Foldback current limiting is used especially in high current regulators. It allows peak load current up to IL maximum but reduces current during overload or short circuit conditions. The green shaded network is similar to constant current limiting with added resistors R5 and R6. To turn on Q2, the drop across R4 must overcome both the voltage across R5 and the base emitter voltage. VR4 equals VR5 plus VBE. Under overload or short circuit conditions, load current rises toward IL maximum. When the condition VR4 equals VR5 plus VBE is satisfied, Q2 turns on. Q2 diverts drive current, so the series transistor Q1 cannot increase load current any further. As output voltage decreases, the voltage across R5 also decreases proportionally. Therefore, less current through R4 is required to keep Q2 conducting. So, as Vout decreases, the load current folds back and drops to a value below IL maximum. Constant current limiting is simpler, but the pass transistor can still dissipate approximately input voltage multiplied by limiting current during a short circuit. Fold back reduces both voltage and current stress, although it can complicate startup into heavy or capacitive loads. A robust regulator is designed from worst-case conditions, not nominal values alone. Work systematically through voltage setting, drive capability, headroom, thermal stress, reference current, protection, stability, and transient response. This checklist groups the final verification tasks: electrical performance, thermal safety, overload protection, and dynamic behavior must all be satisfactory before the circuit is committed to hardware. Series regulators are conceptually simple, but reliable design requires more than choosing an output voltage. The feedback loop must regulate, the pass device must survive the heat and operating conditions, and overload protection must keep the circuit safe. Thank you.